Okay. For our final lesson, we're going to be talking about the binomial theorem. So binomial is an expression that has two terms. We can look at a couple binomials here to a few different powers. X plus y to the 0 is 1. X plus y to the first is x plus y. X plus y squared, we have x squared plus 2xy plus y squared, and so on. And so what we want to investigate is there seems to be a few different patterns going on here as we expand these binomials. So notice that as we move from left to right, the power on x seems to decrease by 1. So that's x to the first, and over here technically we would have x to the 0, which is 1. And the power of y seems to increase by 1. So here we just have y to the first, y to the second, y to the third. And again, over here we could technically say that's y to the 0. Also notice that they get longer as our exponent gets higher, right? And it seems that all the expansions, the number of terms, like in this case, for example, we have 2 terms, seems to be 1 more than the power of our exponent there, right? So to summarize a few of these observations, in each expansion we can say they have n plus 1 terms. X and y have what we'll refer to as symmetric roles, meaning they do the same thing in opposite directions, right? The power of x decreases by 1 in successive terms, whereas the power of y increases by 1. Also, something I didn't mention, the sum of the powers in each term is n. So if we look at that x plus y to the 5th, all of the exponents in each set of terms add up to 5. So 4 plus 1 is 5, 3 plus 2 is 5, 2 plus 3, 1 plus 4, and of course 5. And then note that the coefficients seem to increase and decrease in some sort of symmetric pattern. Okay. Well, the coefficients actually come from a branch of mathematics called combinatorics, and they are based off of this, which is called a combination. And when we read it, we're going to read that as n choose r. And it's just the number of ways you can choose a group of r objects out of an overall group of n objects. Couple different notations. You'll see that NCR notation, and then you'll also often see this notation, this vertical n and r in a set of parentheses that's also known as n choose r, okay? So the formula to evaluate n choose r is n factorial over n minus r factorial times r factorial, where, remember what factorial means? I'll just give an example. 3 factorial would be 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. Or we could rewrite it as 4 times 3 factorial. And so we'll use that in some of our simplifying examples here. So let's do an example where we evaluate different binomial coefficients. I'm going to do the first one by hand, and then I'll show you in your calculator and on Desmos how you can access the combinations operator. So 8 choose 2 based off our formula would be 8 factorial over 8 minus 2 factorial times 2 factorial. So that's 8 factorial over 8 minus 2 is 6 factorial times 2 factorial. All right, so if I want to evaluate this by hand, remember 8 factorial is 8 times 7 times 6 and so on, but I'm going to stop at 6 and just put a factorial there over 6 factorial times, and 2 factorial is just 2 times 1, so I can just say multiplied by 2. Now notice I have that combination, I have that common factor, I should say, of 6 factorial in the numerator and denominator. Can multiply this out. 8 times 7 is 56. Divided by 2 is 28. So 8 choose 2 simplifies out to 28. All right, let's do B. I'll show you in your calculator where you can find that factorial operator at this point. So if I wrote it in the other notation, this would be 10 choose 3. Let's go to our calculator. We're going to go to the math button and scroll all the way over to the probability menu. And you can see the third option down is NCR. Do that. I'm going to enter, one more time. Enter 10, and then after the C, 3, and boom. Get 120. All right, so that's the answer for B. For C, I'll show you in Desmos. Let's take a look. So 7 choose 0. In Desmos, you can literally just type in. It's going to be lowercase n, uppercase C, lowercase r, and then it'll kind of snap to the correct function. So the way you do this is it's NCR, you open parentheses, and then you give it n comma r. So in our case, it was 7 comma 0. And it'll tell you there is one way to choose 0 objects from a group of 7. You just don't choose any objects. So 7 choose 0 is 1. Okay, so this one comes out to 1. And lastly, 8 choose 8. Let's just do this one by hand again. So that's going to be 8 choose 8. So my n is 8. N factorial. My r is 8, so 8 minus 8 factorial times 8 factorial. Whoops. My factorial should be on the outside of those parentheses. All right, so this is 8 factorial over 0 factorial times 8 factorial. Well, 0 factorial by definition is 1. So I have 8 factorial over 8 factorial, which those divide each other out. Final answer is just 1. All right, so that's how we use our combination formula and where you can find it in your various technologies. All right. This is something called Pascal's triangle. So for smaller binomial expansions, you can use Pascal's triangle, which is a pattern for binomial coefficients. All right, so in Pascal's triangle, we start with the tip of the triangle as a 1, and the second row is also 1s. The third row, the way we can obtain that is by adding each 2 successive terms. So 1 plus 1 makes 2. The outsides are always 1s. So now the fourth row, since I have 1, 2, 1, I'll start with 1 on the outside. 1 plus 2 is 3. 2 plus 1 is 3. And then the outside is 1. So hopefully you're recognizing the pattern. So now the fourth row, we start with a 1 on the outside. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And then we end with a 1. So you can continue that pattern. And those actually represent the coefficients on any row of binomial expansion. So for example, you can take a look here. If I have x plus y to the 0, that just corresponds to 1, and the expansion of that is 1. So we call that the 0th row. The first row refers to x plus y to the first. And so since the first row is 1, 1, the coefficients are both just 1. So the second row is x plus y squared. 1, 2, 1 you can see as the coefficients, and so on and so forth, okay? So you can use Pascal's triangle to find your binomial coefficients as long as it's not too big of an expansion, right? If you're doing like x plus y to the, 20th, this would be a pain because you have to start from the 0th row and build your triangle out to the 20th row if that's the expansion you want to do, and that can just get a little time consuming. But let's use the 7th row of Pascal's triangle to find the binomial coefficient. So remember, this top one is the 0th row, and so this one down here will be the 6th row. And so I need to build off the 6th row the 7th row, which is going to be the next row down here. So we'll just do that. We start with a 1. 1 plus 7, that's 8. 7 plus 21 is 28. 21 plus 35 is 56. 35 plus 35 is 70. 35 plus 21 is 56, 28, 8, and then end with a 1. All right, and that corresponds to these combinations. So 8 choose 0 is 1. 8 choose 1 is 8. 8 choose 2 is 28. 8 choose 3 is 56. 8 choose 4 is 70. 8 choose 5, 56. 8 choose 6, 28. 8 choose 7, 8, and finally 8 choose 8, 1. And those would be the coefficients on the expansion of x plus 1 or x plus y to the 7th. Okay. So now we're going to actually do an expansion. Why don't we use the 3rd row of Pascal's triangle to do this expansion? So let me just go back to the other page. So here's my 3rd row. I'm just going to take a picture of that 3rd row. And I'll paste it over here.
Teacher, pardon this interruption. This is the Johnson Senior. Just a quick reminder for tonight, for the senior farewell dinner. That dress is not.
Okay.
But it is strongly preferred.
So let's do our expansion first. So remember, the exponents on x will start at the highest exponent and decrease by 1 with each successive term, and the exponents on 1 will start at 0 and increase by 1 each time. So my first term is going to be x to the 3rd times 1 to the 0 plus, and now they go in opposite directions. So the exponents on x come down by 1, the exponents on 1 go up by 1. So plus x to the 1st, 1 squared, and then plus x to the 0, 1 cubed. Now I'm going to go ahead and put in my coefficients, which we have up here from the 3rd row of Pascal's triangle. So now first one is coefficient of 1, second one 3, third one 3, last one 1. And we can write out our final answer by multiplying everything out. So this is just x cubed plus 3x squared plus 3x plus 1. And there's my expansion. All right. Let's try this one. I'm going to do the same thing. Let's paste my 3rd row. So now what does this look like when it's not just 1 as my second term and it's not just x as my first term, it's actually x squared. Works the exact same way. We're just going to be putting my exponents on x squared and on 4 rather than on x and 1, right? So we'll start with just the exponents and then we'll deal with the coefficients at the end. So my first term is going to be x squared to the 3rd times 4 to the 0 plus, leave some space for a coefficient, x squared. Now that exponent comes down by 1, so squared times 4 to the first, that one goes up by 1, plus x to the first, I'm sorry, not x to the first, x squared to the first, 4 squared, and then finally plus x squared to the 0 times 4 cubed. And then we'll go ahead and add in our coefficients, which are based on that third row of Pascal's triangle. So that's going to be 1, 3, 3, 1. And then to write the final answer, we're just going to multiply everything out. Well, 4 to the 0 is just 1. X squared to the third power of a power we multiply, so that's x to the sixth, right? Plus 4 to the first is 4, but we have that coefficient of 3 as well, so 4 times 3 is 12, x to the fourth, plus 4 squared is 16, but we still have that coefficient of 3, so 16 times 3 is 48, x squared, plus, and then x squared to the 0 is just 1, but 4 to the third, 4 times 4 times 4 is 64. Right, and there's our final expansion. All right, give the group work a shot and the delta math a shot.